We talked about how empty space has energy, and that this is a consequence of the simply probabilistic nature of tiny things. That even the existence of stuff never has one answer. But this is considering how precise you're trying to be. The smaller a time frame is for detecting whether or not a virtual particle exists, we see how our answers vary every time. But by taking the average of all those instances, we know it doesn't actually exist. What happens when that balance that we talked about in the previous video gets thrown off, especially in the presence of really strong gravitational fields? And these gravitational fields, well, they change the physics of regions in space-time. So that's what we're going to talk about today. Hi, my name's Beam, and I'm here to teach you some science. In a previous video, I made a short explanation relating gravity and the entropy of a black hole. And I used that short explanation to give an introduction of what's really going on. This time we're going to be more specific. At this point, I want to first mention that virtual particles are not real particles. They're not actually objects. They are more of a mathematical tool that we use to model how actual particles behave. Stephen Hawking's own explanation of Hawking radiation was, as he claimed himself, pretty inaccurate. Hawking radiation doesn't come from matter-antimatter pairs getting thrown off balance because one of them happens to be near the point in black hole that doesn't let anything escape it. When you try to match the amount of particles that get caught by the event horizon, that value doesn't match the actual Hawking radiation that we observe. First off, when we talk of gravity, we talk about space-time curvature. And if this concept isn't familiar to you yet, I have some videos on that. Let's start by visualizing a region in space-time. And we don't have to go too far. The region near the Earth's surface is more curved than the space-time region further from it. There's a difference with how curved space-time is between these two regions. This also means that the laws of physics are quite different. Basically, the different laws of physics between these two regions means that there's also a difference between the number of virtual particles that apparently come into existence. One of the ways that we relate regions in spacetime is by doing a Bogoliubov transformation. And what this fancy term is just a shorthand for us to describe how particles behave in their respective spacetimes, with their respective physics, with their respective laws of physics. With the transformations, you can see that the number of particles may not necessarily agree with each other. In quantum mechanics, we have these things called creation and annihilation operators, and that doesn't mean that we create or annihilate particles. It's just a tool for us to know how many particles occupy a certain energy level, and so on. I'll explain why they're called creation and annihilation operators in a bit. For different regions in space-time, you can imagine that there would be different arrangements and combinations for the creation and annihilation operators depending on what our system looks like. And for the specific combination we have, we can basically count how many particles are in energy levels 1, 2, 3, and so on. They're called creation and annihilation operators because you can think that we start off with an initial number. And depending on our environment, that initial number can go up or go down. From an initial number of 3 particles in a specific energy levels, we can end up with 1 after our system goes through all kinds of perturbations and such. So as I was saying, with differing gravitational field intensities, our system of particles can be perturbed in different ways as well. In a stronger field, we could end up with the 3 particles going to a much higher energy level. Farther from the region with a strong field, we could have the 3 particles being in the low energy state. Those 3 particles in the higher energy level, we can detect as radiation, and that's Hawking radiation. A straight up fascinating thing about Hawking radiation is that despite the usual image given to us that the particle production process occurs at the edge of the black hole, it actually doesn't happen there. The proof for this is that more often than not, the wavelength that we get for Hawking radiation is comparable to the size of the black hole. So the entirety of the black hole is involved in the process, and that tiny bit of information is illuminating as hell, isn't it? From seeing how Hawking radiation occurs, you'll probably think that Hawking radiation doesn't just come out of black holes, but in any area with differences in the gravitational field strength, and that is correct. Then there's this one last thing I want to mention before I end the video. Scientists have done this cool thing where they observed a vacuum under changing magnetic fields. This pretty much changes the index of refraction of the vacuum. Think of how the speed of light changes before and after it reaches the surface of water. Changing the magnetic field basically does the same thing without actual matter being involved because, well, what we need is a vacuum system. Because the physics of the vacuum changes, once again, there's that disagreement with the number of virtual particles in a system, even though it's the same vacuum system. There are also other concepts around virtual particles that are pretty cool to think about, such as the theory that dark energy is related to these virtual particles that produce the vacuum energy quantity we talked about before. But going back, if there's one thing I want you to get from this video, it's that even emptiness is relative. Two regions of space-time that both have nothing in it but differ in the strength of their gravitational fields can be related to each other with those transformations we talked about. And a consequence of those transformations is Hawking radiation. So I hope you enjoyed this video. Thanks for watching. I'll see you next time. So I got this shiny Quanta in Legends Arceus, and it got me thinking, what makes anything shiny? We know we can see things because of electrons moving up and down their positions in an atom. At first glance, molecular cages sound pretty intense, even though separately we know them well. Molecules what make up stuff, and cages. If you cut your body into its constituent parts and add their masses together, this is of course the same as getting the mass of your body as a whole. For particles, it's not quite the same. Dark matter. Called dark matter because we can't easily use electromagnetic radiation to detect them, as we normally do with other objects. Doesn't really sound like the end of the world to me. I mean, neutrons, protons, and electrons are things we can't see, but we know they exist. Gravity, the reason rain pours downwards and apples fall down trees. But it's also the reason for one of the most tragic ways you can die in a video game.